So I see that a few people have joined now.
Yeah.
And since you are recording, maybe we can begin.
Yeah, I think so.
Okay, so thank you all for being here today, and a special thank to Tobias for staying late and being available to give a talk for us. So he is currently an associate investigator and research fellow since this January at the QUT in Queensland. But before, he was a postdoc and formerly a PhD at the Imperial College in London, and he won a wide range of prizes with his interesting research. I had the luck of meeting him at this year ICDL EpiRob conference. He was giving an interesting talk, and there was too little time for asking questions. So we chatted a bit, and we found out that a very good idea could have been for him to give us a talk with more time to explain his current and former research. And that's how he came here today, giving a talk that is entitled Cognitive Architectures and Bio-Inspired Perception for Human-Robot Interaction. Thank you. So I leave you the stage, Tobias, if you want to share your screen.
Yeah, thank you very much, Alessandra, and thank you very much, Anna, for organizing today's presentation. Great. So I'm really excited to talk about my work, and especially I've done quite a wide variety of different works, but my heart really lies in the cognitive architectures and bio-inspired perception. So I'm half between computer vision research and robotics research. So you will hear both sides of the story. And in the first part of the talk, I'm mainly going to talk about my PhD work, which, as you said, was back at Imperial in London. And then I'd also like to introduce some of the work I've done since joining QUT here in January earlier this year.
Sorry for interrupting. We're just not seeing the slides currently. Okay, I think just a sec. Right now we're just seeing a blank screen, I think. I don't know if Alessandra can confirm. Okay, perfect. Now we see.
Now you can see?
Yes, and if you try to go to full screen, do they still show up?
Can you still see?
We're still seeing the same screen of the actual program. So it could be the...
Now, just okay, now that should help.
Perfect.
Okay, cool.
Okay.
Yeah, before I start as well, if you have any questions at any time, just interrupt me. I'd rather answer the questions directly if it's something urgent. Otherwise, we can wait till the end. So now I cover one particular aspect of cognition and perception in my PhD work, which is perspective taking. Let me give you a brief definition of what perspective taking is. So to me, it's the ability to assume another person's visual spatial viewpoint. So there's a target agent, which is the human. There's a target object, which is shared between the human and the robot. Let me just quickly interrupt my wife vacuuming. Sorry for that. That's the joy of working from home.
It's absolutely normal, no worries.
So now I'm back. Okay, so the definition again. So there are three components to perspective taking. You have a perspective taker. In my case, it was the iCub humanoid robot, which you are all very familiar with. So there's the target agent, and the iCub takes the perspective of that human. And then there's one or multiple target objects which are shared between the human and the robot. And now in my work, as you said, it's very much bio-inspired, and I take inspiration from both psychology and neuroscience. So in this first work, I found a wide variety of works on the psychology of perspective taking. And psychologists have divided perspective taking into two levels. So level one is a very simple level, which is purely whether the object can be seen by the other agent or not. So whether the human can see those agents. And I will show you some examples where this may or may not be the case. And then level two perspective taking, which is really of interest in my PhD work, is acquired around 5 years of age. And it gives the robot then a spatial understanding, so what is to the left and what is to the right of the human, as well as a visual understanding, so what the world actually looks like to the other person. And this is really important in, for example, human-robot interaction. So when we interact between two humans, then we automatically take the perspective of others without even thinking about it. It's important for action recognition, so you can do that from different viewpoints. It's important when you want to understand language, or even for path planning in robotics, where you have to consider where the other person will likely go in order to avoid bumping into that person. And in the talk, I will show you two approaches to it. The first one very briefly, which is like the standard engineering approach. So what are the components that you require in order to solve that perspective taking task on a robotic platform? And then I will focus more on a computational model where you're trying to understand the mechanisms, how humans actually take the perspective of others by using a simulation involving two robotic platforms. But before going there, I'll show you the components which are required, and I will go into depth on some of them. So you need to recognize objects and track objects, and that I do with the just the iCub cameras. You need to estimate the gaze, as well as map the environment. So you have to have some idea what the environment, the whole of the environment looks like in order to take the perspective of the other. And then, given the inspiration from psychologists, I then have two different components for level 1 and level 2 perspective taking respectively. So for level 1 perspective taking, it's a line of sight tracing. So there's a trace, there's a line of sight between the human and each of the objects. And if there's something occluding that line of sight, we know that the human can't perceive that object. And then for level 2 perspective taking, it's a mental rotation. And this mental rotation is what I will focus on as well in the next stages. So let me quickly show you a video how it looks like when applied on the iCub robot. Obviously, everything works in real time. So there are those line of sights. And then, as I said, if something is occluding the line of sight, the robot then knows that that those objects can't be perceived and can take that into account when it's reasoning about those objects. And then visual perspective taking, that gives you an idea of, it gives you a gist of the scene. So what the scene looks like from the human's perspective. So there's really a rotation of, in this case, a point cloud, but it will be more sophisticated later on. So, and then if the human moves around, you can see how this rotated point cloud updates based on the head pose as well as the eye gaze of the human. So this is my very first work, which I presented many years back at ICRA, and but still that was kind of the base for all the other follow-up work on this topic. Now, before I go into the computational model, I want to give you some computer vision-y background on how I estimate the gaze. And I want to do that because this framework is available open source, and it works with ROS, and I'm sure it could be integrated with YARP as well. So we've used it for a couple of robotics applications, and it's just very, very handy to have that. And I know that at IIT, there's a lot of work on eye tracking and understanding the cognitive state of humans. And I think if you can do that using normal camera images, so we can use any camera for that. We could use the iCub eye images or camera to estimate the gaze. I think it's really powerful to then get the cognitive states of the humans. And I will show you some applications very briefly at the end of my talk. So why do we need the eye gaze? Why isn't the head pose sufficient? So why do we look at the eye gaze at all? So when we have a normal conversation, which unfortunately in times of COVID we don't too often have, then it serves as a regulating signal. So when is it my turn to speak? When is it your turn to speak? And also when I want to measure your attention, if I purely look at your head pose, it's not sufficient. Whereas if I can perceive your eyes as well, I can really tell whether you pay attention to what I'm saying or not. And also when I want to recognize actions of another person, if the eyes are occluded, then I'm not as accurate in the action recognition as when the eyes are visible. So the eyes can tell us something about, in any grasping, you typically look first of what you're doing. So when we want to recognize actions, eyes are really, really important as well. And this is a fun application which I found a couple of years back. So apparently you can, when two people go on a date, you can tell whether one person is interested in the other person purely based on the distribution of the eye gaze. So there's really a lot of different applications. And as everything in the computer vision area, eye gaze estimation has been tackled with deep learning approaches. But they have the issue, as we all know, that you need to have a lot of data to train those models. So in the first instance, I proposed a new data set. And why are existing data sets not suitable for human-robot interactions? Because they're very limited in their appearance and especially in the camera-subject distance. So they work very, very well if we look at laptops, but they don't work well at all in normal interactions with the iCub that we like to have. So here are some examples of previous data sets: MPI eye gaze, IDEA, and gaze capture. And you see there's not much variation in the head pose. Everyone looks straight at the screen, which hinders the then inference on in human-robot interactions. And why is that? Why is looking everyone straight at the screen? Because the way they collect the ground truth is displaying a little target, and then you have to follow the target around on the screen. And every time it stops, you press the space bar, which indicates that you look at the target, and then that's like one annotated position. Obviously, everyone is getting a little sleepy after doing that for more than 5 minutes. So there's a lot of wrong annotations in those data sets as well. And it's just not, it doesn't scale very well to human-robot setups. So I came up with a completely different approach for collecting that data, which is, here you see me sitting just on a chair. And you see there are little motion capture cameras. And I wear an eye tracking device. And there are motion capture markers attached to that eye tracking camera. So what we can do is then we get the ground truth head pose by those motion capture markers because they can be perceived. And we get the ground truth eye gaze by the little cameras which are mounted straight under the eyes, so that they're very, very accurate as opposed to if you're very far from the camera. And now that's a free viewing condition, so I don't have to have any particular task. I can just look around and I get annotations at whatever the frame rate of the camera is. So that's really, really powerful because subjects were just able to look around, walk around, do whatever they like. And it gave like really, really good annotations, which are suitable for human-robot interactions because people were actually asked to move around freely, and each subject had like a slightly different area with a different background, so you could generalize as well. But the problem is obviously that you have to wear those eye tracking glasses, and if you do inference on those images, then if you do images, then the training data sets is highly biased towards those classes. And the head pose, for example, the algorithms could focus on estimating the pose of the classes rather than estimating the pose of the head. So we somehow need to get rid of them. We need to remove them from the image. And we can do that because we have a model of the glasses, and we can project down, and we have the pose of the glasses. Now we can project down the 3D model on the 2D images, which give you a masked image where basically like you can stand out the just the glasses. And now we can, using a generative adversarial network, we can now generate images which look very, very similar to the ones, to natural images. So we have two training data sets, one where the glasses are worn and one where the glasses are not worn. And then we can generate images based on basically trying to map the ones where the glasses are worn to the ones that look similar to natural images where the glasses are not worn. The problem is if you just use the GAN generated image, then the gaze will be different, which is obviously not what we want. So what we do is we only inpaint the areas here shown in red, and then the gaze is preserved and the glasses are removed. So there's some artifacts in those images, which we are well aware of, but we've shown that if you train your convolutional neural network now on those images, it generalizes very well to different situations and even to different data sets. So the gaze estimation networks, they're fairly straightforward. I think one of the novelties here is that we found if you ensemble different networks, so just initialize them with different rates and then train them, and then at inference time, load a couple of different networks and ensemble their predictions, you find that the gaze estimates actually improve considerably. And now the overall framework at training time is fairly involved. There's many, many different components. So you have the GAN, you have the some facial landmarks detection to extract the eye images, etc., etc. But the good news is that at inference time, so once it's trained, it's all done. At inference time, it's very simple. You just input an image, you extract the landmarks, so the eyes and the face, give that into the convolutional neural network, and that provides you with the gaze. And as I said before, it can be any source of camera. So it can be depth camera, webcam, laptop, robot, etc., etc. And we tried all of them, and it works really nicely. And let me show you a couple of results for that. So so here's a little animation going on. So you see the bars go up and down. That compares the inpainting. So here, when the bars are up, that's without the inpainting. And whoops. And when the bars go, so lower is better. That's the angular error. Should have said that. So the lower, the better. And then in blue, you see this is our model, and in red are the comparison methods. And regardless of whether you use inpainting or not, our method always performs better than the comparison methods. So there's a 3D angular error of, I think, around 7.7 degrees. So if you map that out, I think over 1 meter of distance, it's something like 5 or 10 centimeters of error. So it's fairly accurate with that. And here are some animations. So on the top, you see one subject from the training data set where we apply our method. So you see, regardless of where she's looking, it follows really nicely in real time again, because we want to deploy it on a robot. And down here, I do some really extreme gazes, so you can see you can clearly see the gaze predictions and how they even work in very, very extreme cases. Now the question is, what can we do with that in a practical setup? And I'm very proud of this work because I think it's really, really powerful when we do that. So here's a subject driving a wheelchair based on just the eye gaze. So you can see his hands are just in his lap. He doesn't use any controllers at all. There's a laptop in front of the subject, and it's just a normal laptop camera. And now the subject can drive the wheelchair based on, well, if the subject looks to the left, the wheelchair is turning to the left. If the subject is looking to the right, the wheelchair is turning to the right, and so on and so forth. And that even maps in, that even works in outdoor scenarios really, really well. So here you see outdoors, completely different lighting conditions. Everything is different, and the subject can still control the wheelchair really well. And that's really important because we know that so in some disabilities, the last muscle which still works is the eye muscle. So it's very much simpler than trying to, the current, I think, systems work with breathing. So if you do, then you go left or something like that. So you can imagine that this can be really powerful for those disabled subjects. Yeah. And now, in addition to gaze estimation, we've also done some work on blink estimation using the same data set. And blinks are really important to detect cognitive load, tiredness, etc., etc. And also gaze estimation methods, they often provide just a random estimate if you don't consider the blinks, which is really, really annoying as well. So they don't really consider what happens if people blink, and people blink quite often in some scenarios. So what we've done here is that we proposed a new blink detection network, and then if the eyes are open, then we provide a gaze output, whereas if the eyes are closed, then we just avoid an incorrect gaze estimate. And we made some first steps toward a unified framework for blink and gaze detection. So where you do it, rather than here in this setup, it's two separate networks, one for blink detection, one for gaze estimation. So we've done some work showing that it might be of advantage to combine the two using some semantic segmentation as well. Cool, so that was the computer vision-y part. Before I go on to the computational model of perspective taking, are there any questions about the first part? All good? Cool. Okay, so let me continue then with the computational model of perspective taking. So I mentioned it at the beginning. The aim here was to understand the underlying mechanisms when humans take the perspectives of other humans. So there's been a lot of work from psychologists to propose different models, but at least I have an engineering background, obviously, and the descriptions they have in their papers aren't quite applicable to come up with an algorithm which implements any of what is stated there. So the aim here was to get a deeper insight into the algorithmic mechanisms where humans take perspective of others. So there's other fields investigating perspective taking, cognitive neuroscience. I just talked about robotics a lot, but there's a lack of computational models. And this as well was the work which I presented at ICDL earlier this year. How I got to talk with Alessandra about this a little bit more. And what I did is that I formalized the embodied transformation account, which psychologists have proposed. So what it means is that perspective taking is a movement emulation, so like a simulation of movements, rather than movement execution. So that means that rather than, it basically means you step literally into the other person's point of view, but you just imagine how it would be like to step into that point of view. And I think that that's really powerful because you can think of many ways of developmental account as well. So how children learn perspective taking, and how their motor model first needs to mature enough in order to be accurate, such that you can do those movement simulations. So the way that psychologists have investigated perspective taking is giving stimuli which look like this. So there is, you see an image basically. So let's consider this middle image here. And then there's this other person looking at two objects. Here it's, I don't know why, but guns and roses are the two objects. And now your task is to decide, is the rose to the left or to the right of that person? And then you have to press a button, either a left key press or a right key press, if you think it's to the left or to the right. And now what you can manipulate is the angular disparity between yourself. So you always look straight at the screen, as probably most of you are at the moment. And then the disparity of that image you're looking at. So now if the other person is looking, having the same perspective, then here, like those are the response times, which you see going from low angle of rotation to the right to higher angle of rotation to the left. And you see that very low angles lead to very fast responses. And now if you increase the angle, so that's going to this direction or to that direction, then the response time increases as well. So that wasn't too surprising to me. So there's some mental effort obviously required to change the, or assume that other person's perspective. Real fascinating thing which I found is that there's a difference on how you look at the screen. So if you now rotate your body, your own body to the right or to the left, that makes a difference in the response times. So if your body is rotated in the same way as the required movement direction, then you're faster, as if compared with the opposite way. So that's really was mind-blowing to me when I heard it the first time. And that now opens very interesting questions in why that is. Obviously, it's not task relevant. So in order to solve the task, it purely matters what the other person's perspective is. Your own body rotation shouldn't matter because you always look straight at the screen. So you always look straight at there. But obviously, there are some underlying things going on in your own motor system, which gives you a prior or like some understanding of what the other person's perspective looks like. And that's, I formalized this now in the following. So the experimental setup, I have two simulated iCub robots. I use oranges and bananas instead of guns and roses, but the task of the blue robot here in this case is to take perspective of the gray robot. It has to decide whether the orange is to the left or to the right of that other person. So then, other robot in this case. So this is how the scene looks like from the two robots. So from the blue robot, the scene looks like this, and from the gray robot, the scene looks like that. And now, yeah. So, and then we systematically vary the posture and the movement congruence. So I will just repeat what that is in a second. And the architecture which I came up with is as follows. It's inspired by Hammer. For those of you who read any papers on this, from Yannis Demiris, my PhD supervisor. So he came up with that model, I think 15 years ago now. And it's basically in parallel, you have multiple forward and inverse models. So the forward model here is just indicated by a little f, which provides you with an estimate of the state at time k+1, given the current state and the a control input. And a control input could be something, it's quite abstract. So something like stepping forward, stepping to the left, stepping to the right, rotating to the left, rotating to the right, and so on and so forth. And now you have different forward models, or for the different control inputs. So you have n different possible control inputs, and for each of them a forward model, and each of them gives you an estimated state. And now what you do is you compare the target state, so we can perceive the state of the other robot, and we then compare that state of the other robot with the predicted state of the robot who's taking the perspective of the other robot. And that results in a distance term, d. And now whatever model comes up with the smallest distance is then executed at this particular time step. And then we do the same thing again. So this state at k+1 then becomes the current state, and we execute it as many times as is needed until we reach a distance which is smaller than some epsilon. And the robot state I should have mentioned is simply the XY position on the planar surface, as well as the rotation of the head pose and eye gaze and body of both robots. And now the important bit so the aim now was to replicate the response times that we observed in human experiments. And in order to do that, I needed to come up with those two terms such that you can calculate the distance. So let me start with the left term first, which is task irrelevant, I should mention. So that's what shouldn't really matter. So that's the nth orientation. So let's say the orientation of the body and of the head pose, just to consider two of them. And you sum each of the individual ones up. So, you know, like it shouldn't really matter whether I look at the screen like this or whether I look at the screen like that, because my overall gaze position is still the same. But here we compare the positions of each joint, basically whether you want to exactly replicate the other robot's pose. And then the right term is the gaze direction, which is the actual task relevant term. So here the gaze direction is basically the sum of all the individual states. So like the body pose, the head pose, and the eye gaze gives you the overall gaze direction. And now you can basically have a mixing parameter which gives you a weighted sum of those two, which results then in the distance. And now we can compare to human data. So I will show you in a little bit how I pick those weights. The first very simple comparison is simply adjusting the angular disparity, how I call it, or the angle of the other human without considering the body pose. And then we find that there's a linear increase in both human data, which is always shown in light colors, and model data, which is shown in dark colors. So here I'm cheating a little bit, shouldn't really have done this, but the human response time doesn't start at 0. So there's some other perception, etc., which is not considered in the model. So in the model, those response times are calculated as the number of steps, so the number of forward models that are executed until you reach the target position. So yeah, both of them are linear, but there's no big surprise, and you could have come up with many different models that have a linear response time as well. So it becomes interesting as soon as you consider those movement, so that's the movement congruence. So now you see that the red robot who's taking the perspective now either has the body oriented in the direction of the movement, of the required perspective movement, or in the opposite direction. And you see that now there's a difference in the response times, which is significant here in both model data on the left and human data on the right. And there's, if you check the paper, or we can chat more in the question time, but there are similar statistical properties in a wide variety of those experiments. So in addition to the movement congruence, you can also consider what's called the posture congruence. So whether then you rotate the other robot's body as well, and that has an impact on the response times as well. And we see that the model again performs very similarly to the human data. And interestingly, so far I just talked about two individuals, let's say like robot number 1 and robot number 2. But what we found in psychology is that different humans have different times to take the perspective of others as well. So the response times differs hugely between different individuals. And the model can also explain those differences in individuals. So what psychologists have found is that there are differences by social skills and gender. And I don't make any argument on that. All I can say is that if you change those weights, which I told you about earlier, very slightly, and instantiate different model instances now with different weights, just drawn from a normal distribution, then you can replicate the embodiment scores of humans. So what's an embodiment score? It's a difference of the congruent and incongruent response time. So when your body is oriented in the proper direction and in the wrong direction, just take the difference between those response times. That's the embodiment score. And what you see here is that each little dot is one instance of a human in dark or model in bright. And you can see that the embodiment scores very, very nicely match between that. And there's, again, no statistical difference between human model data for the female data, for the male data, or for the combined data either. And what you see is that there are some individuals which are classified as embodiers, which have an embodiment score larger than 0, and some which are classified as systemizers, which have an embodiment smaller than 0. And what I haven't mentioned in the ICDL talk, but I want to talk about now a little bit because I find it really interesting, is that the model data only matches those of the embodiers, which means that they actually, like those humans, simulate that. So the model proposes that those humans simulate this other perspective. Whereas systemizers, they could purely remember. So they can have a memory just based on memory without actually transforming their perspective to the other perspective. So the model can't replicate. If you include all of those, then the model data doesn't hold that anymore. But if you exclude them, then the model data agrees between humans and models, which suggests that if you now extend the model with such a memory strategy and apply that every now and then for some individuals, then you could also replicate the data for those systemizers. So that's something we could maybe chat about if you want to. And now the good thing about having a model is that you can predict things which are really hard to replicate in normal experiments with humans, because you can't actually stop them at certain times. For example, the model predicts that if you force an early response, then that leads to an egocentric bias. So you give the same response as what you see from your own perspective. Or secondly, the model also proposes that there's a habituation effect. So you get used to the same trial. If there's 2 consecutive trials with the same required movement direction, then in the second time you're faster because the right model is preloaded. So you remember there's different forward models. The model states that if you execute the same forward model in the next step, then that's cheaper than having to load different forward models, because only a subset of the forward models are executed at any time. And interestingly, there was one article published a while back now in the Cognition Journal, which supports that argument which we make about forced early responses. And I'd like to briefly mention some of my other work on cognitive architectures, because that was in the title as well. But I only want to briefly mention it because IIT was actually involved in that work. So this is on DAC, so distributed adaptive control. This is with Ugo Patacini and Giorgio, as well as Franck, who knows him. I think he's now in Hamburg. And what we did there is we proposed that robots could be either very proactive in acquiring new skills or waiting until the human actually kind of tells the robot a new skill. So what we've done is object learning, for example, or learning about the body parts of the robot. So what is called an index finger and so on. And you can either learn that you can either ask the human partner, oh, what is this object? Or you can wait until the human tells you those object names. And there's an interesting trade-off between the knowledge acquisition and knowledge expression. And if you want to chat more about that, I'm not sure how much you are aware of this work, but I just wanted to mention it very briefly. And then we've done quite a variety of really cool experiments on that. But considering that I'm slowly running out of time, and I'd like to chat with a couple of questions about here. I'm going to get really short. And I'm going to keep these ones short as well. So this is a couple of more works which I've done at Imperial, but I want to briefly talk about some work that I've done recently here at QUT. So my first paper here was on event-based place recognition. So place recognition is the task where, imagine you have an autonomous car which is going along a route once, and then it's building a map of that route. And then you deploy it at a different time of the day or different season, maybe half a year later, and you want to recognize whether you've been at this place before. And what I've done in this first work is propose a method to do that using event cameras. So event cameras I know are very popular at IIT as well, so I'm not going to talk too many details about that. But they're really interesting for that scenario because they have a really high dynamic range, are very well suited for different lighting conditions as well. So that's one of the proposals there. Another work which I'm really enthusiastic about is a submission to a conference that I'm not allowed to tell you which conference it is, otherwise I would breach the conference rules, but maybe you know which one it is now. So that's a work on what we call locally global features. So place recognition has often been tackled with the vector of locally aggregated descriptors. So it's a technique to basically describe an image. And what we've done in this work is rather than having a global descriptor, how it's typically done over the whole image, we extract those vectors for small parts of the image and then do a nearest neighbor search. So the idea itself is quite simple, but we found that the results are really, really amazing and vastly outperform the current state of the art. Then I've also done some work on teach and repeat algorithms. So the cool thing here is that we can teach on a little Miro robot, which is like a toy rabbit, and repeat it on a jackal, or also on more place recognition. So it's a place recognition lab where we pick the right reference traversals. But with that, I'd like to thank you very much for listening, and I hope we still have some time for questions. Thank you.
Thank you very much, Tobias, for the... Okay.
Thank you very much, Tobias. Are there questions from the audience? For those of you here, I would suggest to come here for just the organizational purposes. If not, I would just start with a curiosity about the visual perspective computational model you presented based on embodiment. You showed that actually the position of each and every joint, in some sense, count together with the information related to the eye's direction. I was wondering, are you giving the same relevance? Does the model give the same relevance to each and every joint, or have you experimented thinking of, let's say, assuming that there are different weights or different importance of different parts of the body?
Actually, that's a very good question. At the moment, I use this.
Alec, can you mute yourself?
Sure, sorry.
Sorry, I'm just trying to go to the slide. Here we are. At the moment, they're all the same weight. I've never thought about it, to be honest, but that's a really interesting proposal. So here, I think there's only 3 joints at the moment, which is the overall body pose, the head pose, and the eye gaze joints. But yeah, that would be interesting to consider. I haven't done it, but that's definitely something which would be interesting, because I agree, yes, if you think about it, there's probably some joints which have a larger weight than others, as well as some joints which are much easier to move than others. So one of the works that I never got around publishing is on learning those forward models and then having a developmental approach about how accurate do your forward models need to be in order to take another person's perspective. And I think that ties into that question as well, because it's easier to predict some changes in some joint states than it is from others. So yeah, that would be interesting.
I was also thinking if this could be connected in some sense to the action you might want to do with those objects. So I was wondering, maybe to fetch the banana in your example, the torso and in particular the arm could be very important in a goal-oriented ways, whereas maybe the legs less. And so I would. That's why I thought of this different reweighting, and indeed, a developmental approach to get there could be the right way to go. I see another question by Stefano. So I turn off my mic.
Yes, can you hear me?
Yeah.
You have presented these experiments in the framework of human-robot interaction. But maybe I was thinking about that we could set up this discussion in a robot-robot interaction method. I mean, I don't know if the iCub's eyes move around or stay fixed in some direction. Maybe you know that.
Yeah, they can move around.
Okay, so I was thinking about in a setting of continual learning, that is, as you may know, in a setting where a deep learning or a machine learning model continue to learn from the environment around it. I was wondering if we could take 2 iCubs and make the iCub A trying to predict the eye gaze of the iCub B. Then the iCub B, as a robot, could send some sort of wireless information to the iCub A that make the job of a label for the iCub A training. I don't know if it is clear.
I would love to do that. That's really, really cool. Unfortunately, the computational model here, I think that was one of Anna's questions at ICDL. It was only implemented in simulation.
Yes.
So I think the first step would be replicating those experiments in human-robot interactions. And then as a next step, I think it's really interesting to do the same setup here with 2 robots. It might actually be simpler than human-robot interactions.
Yes, I think.
Yeah, so that would be really cool.
Initially, you mentioned that the lack of data was and maybe is a problem, as usual in deep learning experiment. So I thought that this setting of the experiment using robot-robot interaction could perhaps solve this lack of data problem. Because you can take 2 iCub and say, okay, train each other with your eye gaze.
Yeah. The question then would be, how well does it generalize to humans, or would you never apply it to humans?
Yes.
Yeah. But yeah, unfortunately, we only have 1 iCub in London.
Okay.
And that one was only working a third of the time. So,
yes.
But yeah, at IoT, that would have been definitely an option. Yeah, it sounds very interesting, your proposal.
Okay, thank you.
I have a couple of questions if nobody else wants to jump in. Just a sec before my laptop dies. Okay, so one is a bit more of a technical question, and the other one is a broader and delving into the philosophical aspect of cognition. So for the more technical, for the embodiment score that you mentioned, so I have here reference slide 14 and 17 when you're reporting the results for the response times. Is the embodiment score calculated just from the orientation of the person, regardless whether it's clockwise or counterclockwise, or it's a combination of these two? For instance here, yes, because you have the results for the angular disparity, but I'm assuming they're considering both the clockwise and counterclockwise, and that's how.
Yes, so this is what happens here, right? So here in the congruent condition, the body is oriented clockwise, and the required movement direction is clockwise as well. That's why it's congruent. So you could imagine if it was counterclockwise and a counterclockwise direction as well, then that would be considered congruent as well. Okay.
And instead, for the orientation of 0 degrees of the body, how are the results reported? Or here it's just these two?
Just these two here. You can do the same for 0 degrees, which is basically, it falls back to the first slide here, where you have 0 degrees. But you can mix them in here as well. I think in the paper, they should have the ones for 0 degrees as well. I just left them out here because this is kind of in the previous slide here, that's the 0 degree case. And now those are the congruent and incongruent types. But it basically lies right in the middle there.
Yeah, which makes sense. It was just exactly for the mode of calculation. Okay, thank you.
Yeah.
The other one would tie in also with the discussion we had at ICDL, where we were talking for essentially evaluating the computational models on simulated versus physical robots. So since back then I asked you more on the physical side, why don't you use physical robots? Now I would like to ask you, what do you think are the biggest advantages in using simulated robots for this kind of models, if the end point would be then to have them implemented in a cognitive framework for physical robots?
So the advantages of simulated robots here is that if you consider those response time differences, they're quite small. So if you did it on a physical robot, there would be errors in the perception, and the errors in the perception, they might be causing differences in the response time, which are larger than the differences here between congruent and incongruent movements, which would mean that you have to have a really large sample size. So that's one of the disadvantages if you were to do it, if you were to do this particular experiment on a physical robot. I totally agree with you though that the model itself, obviously, the aim should be the deployment on physical robots. And then that's a shortcoming of this work, that it wasn't done. I think the importance here is that you learn about the human side of things. What is important when you interact with humans, right? That can tell you, the model can tell you things about that. So there might only be slight differences in the interactions that you need to adapt. And I think we are very far away from having mature algorithms for the interactions themselves. So it might be that it takes another, 5, 10, God knows how many years before we can actually use those differences in order to adapt our interaction with those with humans. So let's say we recognize that the humans has a congruent has to take the robot's perspective, and the robot is in a congruent movement direction. Then you could adapt. You could ask the humans faster. Could ask him questions earlier, because you know that the times required are lower for those movement directions. That would just be one particular case. I hope that makes sense. I think that there's always, two sides of the coin. You can look at it purely from whether you want to replicate those experiments that the psychologists have shown. Then I think it's much easier and more informative in simulation, because just applying it in the physical world would only add noise, which would make the evaluation harder. But then the other side of the coin is that the aim should be really deployment on physical robots.
Absolutely. Thank you. Are there any more questions from the audience?
I have one curiosity related to the first part of your talk. So related to the eye gaze detection. In the training phase of your system, you're also using RGBD camera, which is then, why are you, I just missed, why are you needing that in that part?
So you here, RGBD camera.
Sorry, correct. Thanks.
Okay. I think it was because of the alignment of, so the RGBD camera allows you to perceive the motion capture markers as well, which is then important to project down the glasses on the image, if I recall correctly.
Are you using also the depth value from the RGBD camera in the training?
No.
Okay, because that's something that then you would lose for the inference if you're using a laptop camera. Or...
Yeah. I think it was just to project down. I think it was because of the relative poses between the motion capture system, the camera, and the eye tracking glasses. And if I remember correctly, it was easier if you had the depth information available. So that was just in the setup, basically, of the whole system, but not in the actual training of the networks.
Thank you. And as a follow-up, in this RT gene, do you see an asymmetry in the accuracy for horizontal and vertical movements? Because this is what we faced with our system or previous system, in which we tried to read gaze from human eyes, and we always ended up having more accurate estimation in horizontal rather than on vertical movements. And I was wondering whether this applies also, or whether this approach avoids this issue.
To be honest, I haven't checked, but I didn't observe any major differences that I can recall. So if you just do it, it's a very scientific approach, and look at the video here, then I can't. So this is like vertical movements there and horizontal movements there. I'm looking at myself there, sorry, in the bottom left. And it seems like it's working okay for both of them. I couldn't, like, I didn't remember. At some point I had the distribution. So in the paper, there's the distribution of the gazers in the training set. And I would think that if they are well covered for both horizontal and vertical directions, I don't see why the network, actually, well, the eyes, there's more white around the pupil for the horizontal direction. That's why it might work better in that direction. I could simply do the inference on the test data sets and then report separately for horizontal and vertical angles. I haven't done it, and the reviewers haven't asked me as well. But yeah, it's a good point. I couldn't tell you, but I don't think there's a big issue.
Yeah, I mean, if you didn't notice it openly just by watching the results in general, and also from the video, probably it's not as large as we faced it in the past. So
yeah. Feel free to try it out. All my code and data sets are available online. So just check my website and let me know if you have any issues in setting up the models.
We have another question from Carlo.
Yes, thank you. Can you hear me?
Yeah.
Okay. I have a more theoretical question. I was wondering whether in perspective taking, the difference in response time between the congruent and the incongruent condition could be explained in a certain way with the concept of self-other distinction. So in the incongruent condition, there is a more deep distinction between the self and the other, while in the congruent one, a fewer.
What do you mean by self-other?
Yeah, when you show the cognitive architecture, I saw that you put the a self model. So a part of the self is the self-other distinction. So the distinction between myself and another person. So if maybe it is quite difficult to find a phenomenon which show the self-other distinction. Maybe the difference between the congruent and incongruent condition can show this. This is my idea, but I don't know.
Right. Yes. I think implicitly this is your self-other distinction you're talking about, isn't it? It's basically so the target position never changes, right? The other robot remains in the same position the whole time. So then the only variable is how do you change your own pose in response to what you perceive from the other. And then I guess, yes, there is a self-other distinction where the poses kind of don't match in the incongruent task, and that tracks down from the very beginning, right? You basically say that the poses are more different. So in a way, you are correct. Yes, you are correct. The question is then, though, still, how do you actually take the perspective? You have to have some kind of mechanism of then, given those different body models, like the embodiment of the other person, still there needs to be some mechanism to actually perceive what the world looks like from that other point of view. So I think it's the same thing we are talking about, just in a different language, maybe.
Okay, thank you.
Yeah, I think, yeah.
I will focus on this part to understand better if it could be. It's an idea that came to me right now.
Okay.
hearing this. But thank you. That's interesting. Oh. Very interesting.
So members of our group are actually doing work also from a cognitive point of view, and also a bit of a philosophical, let's say, on the self. So the concept of self, and also how then we, I suppose the bit of the clash here was the super engineering versus super philosophical concepts trying to reach a common point. However, yes, I think that exactly what Carla was asking can be seen on a very computational level also here in the model. So some very basic representation, of course, because the true sense of others in the self is a lot more complex than this, I think. But it's nice to see that even in a model that is focused on one small aspect, you still have this inclusion of the other, which is very, very cool to see.
Like, obviously, you know, perspective taking is just one of very many components, as you said, which are required for proper cognition in robotics. So I focused on perspective taking there, but I acknowledge that there's many other things which somehow have to work together, and that's kind of what we tried more or less successfully in the model with what I showed very briefly in in this model with they worked with Giorgio and others, with Paul Verschu as well. So DAC, obviously, I don't know whether you might be familiar with it, but this is like a more philosophical approach, and how you put the engineering components into that model here. That was really the aim of DAC H3, so human robot interactions number 3. There were 2 previous models to that. And here, one of the ones is the self, and then there's the will and the actions, and you have those different layers. So there are many alternatives to that particular model, but it was one of our attempts to bring together those different components. So perspective taking here is like a small little bit and piece, but also to me, because it really showed which other aspects there are in getting a working interaction actually on a larger scale, where you can interact with the robot on not just one aspect, but many different, you know, like that there were retrospective things involved as well. So that was really cool. And I think there's a lot more work required or input required from the philosophic aspects. And I think us as engineers, we have to learn a lot more from that kind of world. I think we are sometimes a little bit ignorant about those things, but there's a lot to learn. So it's really good to hear that, you know, like you tackle the cognition aspect from a wide range of different fields.
That's the goal of iCog as an initiative. It has to be a very multidisciplinary approach, because it's not something that's solved just by engineers or just by philosophers or just by neuroscientists. It has to be a joint effort, and that's why we were especially so happy to have you as the opening talk, let's say, of the series of invited events, because I think that you're also working in this area, and the work that you presented fits in quite nicely.
Nice. That's good to hear. Yeah, I'm excited that I don't think there's many groups who take on that effort. So it's good to hear that someone is doing it. It's great. I look forward to hearing more, well, reading more about your research as well.
Thank you. I think that if there are no more, go on, Ala.
So yeah, I was noticing that if there are no further questions, we might leave Tobias to sleep, theoretically, if the baby allows. And I want to warmly thank you for both for the availability today and the availability to keep also the talk recorded, so that we can share and discuss it further. And maybe we will contact you when we try to apply the models or read the papers further with additional questions. So wait wait emails from us.
Yeah, that would be great. I look forward to hearing from you. And hopefully one day COVID will be history and we can see each other at a conference or at IoT. That would be great.
That would be lovely. Ale, I will just ask you to keep Teams active a bit longer so we can save the recording, because for some reasons for me it's blocked at 21. So let's not risk losing it accidentally. Okay. Thank you very much everyone for participating, and thank you, Tobias.
Thank you very much.
Have a nice night and talk soon.
All right. Yeah. Thank you.
Bye-bye.
Bye.